Okay. So in particular, for a simple random sample, the random variables involved are not independent, because if they were independent, this covariance would be 0. There's some mild dependence between them. We can use that to compute variance of the sample mean. And I think we might have done this, I can't remember. Did we do this? Okay, let's repeat it. I'll do it in 2 steps. Okay, the variance of a sum is the sum of the covariances over all possible i's and j's. And from this and this, we can see there's a difference between when I and j are the same. If I is equal to j, we get this. If I is different from j, we get this. So we should split this sum up into I and j the same. And then the covariance of xi is just the variance. And then we look at the terms I different from j.
We can't really put a, like that first term goes to n, but the second one, we know it's going to be.
Oh yeah, I should put here I and j equal 1 to n, but I different from j. Is that what you mean? I should put the limits there?
Right, I guess. We had said that the first term was going to give us n terms, and the second term was going to give us the n squared minus n terms.
Right, yeah. And that's because in the second one, we don't include the diagonal, which has n terms. It's good? Okay. And so we get 1 over n squared. Here, every term is sigma squared. N of them gives n sigma squared. Here, every term is minus sigma squared over capital N minus 1, and there are n times n minus 1 of terms. Why are there n times n minus 1 terms, or n squared minus n? Well, in the previous sum, there are n squared terms, little n squared terms. We separate out n of them here, so that means that n squared minus n must be here. And if we combine, we factor out a little n first. And well, let's factor out a little n and a sigma squared. So I factor this out, and this, and this, and this. That leaves a 1 here, and an n, little n minus 1 over capital N minus 1. So that's the variance of x bar. The sample variance then, or the variance of the sample, random sample, or the variance of the mean of the random sample is that. Okay, the square root of that is sometimes called, in the book, called the standard error. This could be rewritten a little bit. By finding common denominator and combining these two. The common denominator would be capital N minus 1. So we'd have capital N minus 1 there, divided by capital N minus 1. When I combine, the denominator would be capital N minus 1. What do we get in the numerator? Yeah, capital N minus little n, because here we're subtracting this. So actually, we're adding a 1 in the numerator, right? And then we have a capital N minus 1, and the 1's cancel. So you get capital N minus little n. So this is another way of writing that. OK. So if we're faced with a problem of trying to measure the population mean and population variance, or population mean, we might want to find a confidence interval, or some interval that would contain the population mean with a high probability. Okay, so we want to find some sort of estimate for the population mean mu. This is called a confidence interval. Okay. As opposed to a point estimate. Okay, so the approach is to use the central limit theorem. Can you read my writing? Mostly? Okay. If the sampling is done with replacement, you get an IID sample. And if we knew sigma squared, then for large n, the distribution of that is approximately normal with mean 0 and variance 1. Yes?
Is that with or without replacement?
Oh, with replacement. That's a with. That circle is part of the abbreviation, but not an O. So maybe I should write that out. That's with replacement. That's a great question. It's an important distinction here. If it's done without replacement, then they aren't independent. That's the simple random sample. But if it's done with replacement, you throw back in, you sample, you throw it back in, you try it again. then the distribution will be the same on every trial. But if you keep one out, then it changes the composition of the population, and then the distribution would change. Okay, so here, suppose mu is unknown. But sigma squared is known. We have this approximation. This is approximately a normal random variable with mean 0 and variance 1. So the distribution function for that random variable is the normal distribution function. Now, last time I introduced this notation from the book, z alpha over 2 means the following. Here's the normal density. The shaded area is alpha over 2. Z alpha over 2 is a number on the real line, so that the area under the graph of the normal mean 0 variance 1 density to the right of that point is alpha over 2. Okay. Now, what is this part? It says that absolute value, think of this as being the z. It has this density. This means that the random variable has absolute value less than z over 2. So that means it's trapped between z over 2 and minus z over 2. Okay, so let me put minus z over 2. I'm sorry, I said z over 2. I left out some words there. Z of alpha over 2. Okay, this random variable would be between z of alpha over 2 and minus z of alpha over 2. Okay, so we're looking at the probability that the random variable with the approximately normal distribution is between here and here. What's the probability that a normal random variable is between these 2 points? 1 minus alpha, because it's 1 minus the probability it's outside of that interval. What's the probability it's outside of the interval? Well, the probability it's to the right is alpha over 2. The probability it's to the left of this is alpha over 2. So the probability that it's outside is alpha, so the probability it's inside is 1 minus alpha. Okay, okay, so that means with probability 1 minus alpha, this random variable is between here and here. So with approximately probably 1 minus alpha, okay, or if I solve this inequality for mu, So with probability approximately 1 minus alpha, mu lies between here and here. So in the case when sigma is known, we could take a sample, compute x bar from that sample, find the z that corresponds to alpha from the table 2 in the back of the book. Assume you'll keep your book and you'll have it always with you. If you ever want to compute a confidence interval, it'll come in handy. So you could probably sell the book back and look it up online. I wonder how much you can get for your books. Anyway, so this is the interval from here to here is called 100 times 1 minus alpha % confidence interval for mu. Probability that mu is between the two endpoints is 1 minus alpha, approximately. Okay, so let's make a little change. What is sigma over root n? Sigma over root n is the variance of x bar. And does everybody know what I mean by CI? Confidence interval, right?
That's because we're doing a with replacement, right?
Yes, we use this. Where did we use that? We're using. Where did we use that? It's with replacement when we applied the central limit theorem.
IID, right?
Yeah, you need IID, mean finite variance. So we use that here. Let me just reword this a little bit. Since the variance of x bar is sigma over root n, we can rewrite the confidence interval like that. Okay, I just replaced the sigma over root n here and here with the variance of x bar since they're the same. This is in the case of sampling with replacement. Pardon? Oh, thank you. Yeah. So I better put that here. Yeah, here. Sorry. Okay. Notice there's a difference between variance of x bar in the case of sampling without replacement, that's here, and with replacement. With replacement, that term's gone. Without replacement, that term's here. Yeah?
Why did you put the square root again?
Because it's sigma over root n here.
Oh.
Look over here.
Sigma.
So let's think about what this would be when you have independent random variables. This factor's not there, right? So the variance of x bar is that. I want sigma over root n, so I'd be the square root of the variance of x bar. Okay, that's fine. Is that it? Okay. Okay. Now let's pass to the case of sampling if these are a simple random sample. Now we're sampling without replacement. And as is typical, mu and sigma squared are unknown. we still want a confidence interval for mu. Okay. Okay, well, if the population is large, I guess I erased it, but the dependence between xi and xj is very small if the population is large. Remember, covariance of xi, xj is minus sigma squared over capital N minus 1. If capital N is very big, that dependence is very small. And there are versions of the central limit theorem that still hold. So the central limit theorem will still hold. Provided little n is large, but capital N is much larger. So in the case of a big population and a pretty substantial sample size, but not big enough to be close to capital N, then there's still enough randomness and lack of dependence so that a central limit theorem still holds. The central limit theorem would still hold. That is, that expression would be approximately normal. And so we could go through all these steps and finally arrive over here. And have this be a confidence interval where variance of x bar is this, but there's a flaw in using that as a confidence interval. You have to be able to compute it. You have to be able to say what get an actual number, a left endpoint, right endpoint, where the numbers are known. But this and this have a sigma in them, and we don't know sigma. So we have to find a way to estimate variance of x bar. We have to find a way to estimate variance of x bar. Okay, so what we need and the only thing we have is the sample, so we have to use the data from the sample somehow to estimate variance x bar. And by unbiased estimator, do you remember what I mean? That means that whatever I use for the estimate, it's going to be some function of the data. The expected value of that should be the variance of x bar. In other words, the expected value of my estimator should be this. Okay, so I'm going to we have to come up with some function of the xi's that looks like it'll estimate variance of x bar, and its expected value should be this. Okay, and then we're going to replace variance of x bar in here by that estimator. Well, let's start with sigma hat squared equal to 1 over n sum I equal 1 to n xi minus x bar squared. This is the average squared deviation from the mean. Average square deviation from the mean. This is the deviation from the mean squared for the ith random variable. When you add them all up, add up all these squared deviations and divide by n, that means you're taking the average. This is the average squared deviation from the mean. from the sample mean. Okay, so this should be capturing somehow what the variance of x bar is. Let's compute its expected value. Oops. We've done this kind of thing several times. Remember, you can expand the square here, multiply that out. Okay, now when you add them all up, first you'll get 1 over n times the sum of the xi squared. What will you get when you add up this part? Let's do it without this first. Okay, we'd get the sum of the xi squares minus 2n x bar squared. Is that right from here? Because the xi, sum of the xi's is n times x bar, and there's another x bar. And then we get n terms here, so it'd be plus n x bar squared. So this would be the sum of the xi squared minus n x bar squared. Okay. Are we good? Okay. Well, let me exchange sum and expected value here. Here I get an expected value of xi squared. And we've done this computation already. What's the expected value of xi? It's mu. What's the variance of xi? It's sigma squared. We did this computation already for a simple random sample. And the variance of, and so what's the variance? It's the second moment minus the first moment squared. That's kind of thin here. Second moment minus the first moment squared. In other words, the second moment, xi, expected value xi squared, is the variance plus the first moment squared. And the first moment is mu, so we get that. So every term in that first sum is sigma squared plus mu squared. This is just saying the second moment of a random variable is its variance plus its mean squared. Or that's just another way of saying the variance is the second moment minus the first moment squared. Okay. So every term here is sigma squared plus mu squared. And then over here we have n times the expected value of that random variable squared. So it'd be its variance plus its mean squared. What's the variance of x bar? Well, I'll write it this way. And what's the mean of x bar? It's mu. Okay. So now we add this up that many times, that means we get n times this, but then we divide by n, so the first sum after multiplication by the 1 over n becomes this. Then we multiply 1 over n times this, we get minus the variance of x bar plus mu squared. Now we know what variance of x bar is, if we know in terms of sigma squared, that is. The mu squareds cancel. And let's use this expression here. Okay, sigma squared 1 minus capital N minus little n over little n times capital N minus 1. We can simplify that a little bit by finding common denominator. So the common denominator would be this. And up here, then, we'd have that term. So let's see. In the numerator, we'd have little n times capital N minus 1 minus capital N minus little n, which would be little n times capital N minus capital N, because here we have a minus little n, and here we have a plus little n, so they cancel. And if I factor out the capital N, I get little n minus 1 times capital N. So in the numerator, we get little n minus 1 times capital N. So everybody see what I did? It's okay? See, this is what you'd get. When I combine these two, I get this. I rewrite 1 this way. When they have a common denominator, I have to subtract this numerator from that one. And the little n's cancel. And so we get that. So this is the expected value of sigma hat squared. Okay, let's remind ourselves what was our goal. We wanted to find an unbiased estimator of the variance of x bar. That is, we want to find some expression whose expected value is this, or this, I guess. We found something whose expected value is that. It has a sigma squared in there. If we just multiply sigma hat squared by something that depends on n, the appropriate thing, we'll get the right estimator. So we want to find a number c depending on n, so that expected value of c n sigma hat squared is equal to the variance of x bar sigma squared over n capital N minus little n over capital N minus 1. Okay, we want to multiply sigma hat squared by something so that we get that. Or let me just say it's a number c. Okay, I don't have to put n here. Okay, so what would it be? Expected value of c times sigma hat squared is going to be c sigma squared little n minus 1 times capital N over little n capital N minus 1. And we want this to be equal to this. Okay? Okay, that's what we want. This is the variance of x bar. And we want an unbiased estimator. Then our unbiased estimator, if we can arrange so that these two are equal, then C sigma hat squared will be an unbiased estimator. Of variance of x bar. Unbiased estimator means the thing it's supposed to estimate, it has its expected value is equal to the thing it's supposed to estimate. Okay, so we just have to solve this for C. Okay, so first, I guess we can cancel the sigma squareds on both sides. Then we can cancel the little n on both sides. Then we can cancel the capital N minus 1 on both sides. And then if we just divide by this number here, we get that. Okay, so here's our sigma hat squared. Let's multiply it by this C. And what do we get? By rearranging things, I think it comes out to be this. I put the n minus 1 in front of this thing. This 1 over n comes out here. And then the rest of C goes over here. I think I've accounted for everything. And reason to do this is the thing in parenthesis we know already. That's our friend S squared, which in the independent case was the unbiased estimator for the variance over little n times this thing. I guess I could rewrite that as 1 minus little n over capital N. So this thing is called S squared. We've defined that already. So our unbiased estimator is this. So let me summarize. This was what we call the sample variance. And this is still called the sample variance. In the independent case, or the case of an infinite population, the unbiased estimator would be the sample variance over n for the variance of x bar. But there's this population correction factor in the case of a finite population. Okay, so in the end then, what is our confidence interval going to look like? So we replace variance of x bar by the unbiased estimator for it. And I think in the book they give this a name. Sx bar squared is defined to be this. That's it. 3 lines means defined to be, or is, that's the definition. Okay. I could put Sx bar here, I guess, because it's simple. Okay, so everything in here can be computed from either the data, the sample, or the table for normal distribution. See, x bar and S sub x bar are computable from the sample. So you can actually compute everything in here if you know the sample. Up there, you couldn't do it because you had the variance of x bar, which was a function of sigma squared, and you don't know sigma squared, so you don't know what to put in there. So we replace it by something we get from the data, an estimator. We estimate variance of x bar by S sub x bar squared. We replace the variance of x bar by its estimator, unbiased estimator, and that'll be the confidence interval. Okay, so let's take a break, and we'll do a CI when we get back. And there'll be an adjustment to what problems are due on Monday. We haven't covered all the material, so I'll reduce the problems you have to do. Okay, let's do one little refinement of this to a very important case, the dichotomous case. Okay, then instead of mu, we use the notation p hat for x bar. And this is an estimator, unbiased estimator for the true population proportion. That's capital N here. And what would S squared be in this case? So what are examples of this? You want to know what proportion of the population prefers, say, chocolate ice cream to vanilla. So each individual gets a 1 if they like chocolate better than vanilla ice cream. They get a 0 if they like vanilla better. And then you sample people and ask them, do you like chocolate better or vanilla? And if they say chocolate, you give a 1 to that person. You get a 1. If they say vanilla, you get a 0. So this would be the proportion of people that prefer chocolate to vanilla. And then there are more important examples, like when do people respond to medications? You might assign a 1 if a person recovers from an illness, if they're given a medication, and 0 if they don't. And so p hat would be the proportion of the population of your sample that recovered when given a certain medication. Another example might be public opinion polling, more serious than, well, it's hard to say what could be more serious than ice cream preferences, but maybe presidential elections. Okay, so what would S squared be in this case? This is still true, right? That didn't depend on dichotomous or not dichotomous. And now, what's p hat? It's 1 over n times the sum, so this sum must be n times p hat. Do you agree? The sum is n times p hat. P hat is 1 over n times the sum, so yeah?
You mean technically start with xi squared. Sum of the
Oh, xi squares. Oh.
I know that's the same as.
Yeah, no, that's an important point. Xi, the thing that happens here is xi squared and xi are the same. I skipped a step. Xi and xi squared are the same. Why? What about 0 or 1, right? And if you square 0 or 1, what do you get? 0 or 1. Right? So this is the same whether I have xi or xi squared here. So, okay, so what I said at first was, I said this is the same as in the, whether it's dichotomous or not, that's true. Whether the xi's are from a dichotomous population or not, this is true. If they're from dichotomous, that's true. Because when you square 0, you get 0. When you square 1, you get 1. So xi squared is xi. Okay? And so the first term becomes n p hat. X bar is p hat. We're squaring it, so we get minus n p hat squared here. And so this becomes n over n minus 1 p hat times 1 minus p hat. Okay? And so what would our estimator be for dichotomous? Still, well, this would still be the estimator for variance of p hat. Well, we substitute that for s squared. You notice there's a little n there. And we're dividing by little n here, so they cancel. So we get p hat, 1 minus p hat over n minus 1, and then this correction factor for finite population. So in constructing confidence intervals in the dichotomous case. What would we get? Well, x bar is p hat. And then s sub x bar would be the square root of that. And that's the CI. Okay. So there's an example in the book. Example C, page 213. Says that P is supposed to be the proportion of hospitals that had fewer than 1,000 discharges. And it turns out it's 0.654.
We know 0.654 because we know the population, right?
Yeah. And that was in, I think, not that it matters, but it was in 1 month in 1968. So that's the true value of P. Pretend you don't know it. I didn't tell you that. Okay. A sample of size 50 was taken. I think it was 50, sorry. Yes. And 26 had fewer than 1,000 discharges. So this means, what about p hat? Yeah, so it'd be 1 over n times the sum of the xi's. Xi's are 1 or 0. 1 if they had fewer than 1,000 discharges, 0 otherwise. So it'd be 1 over 50 times 26, or 26 over 50, which is 0.52. Is that right? I think, pretty clearly. Okay, what's the estimate of the variance of P? Or P hat, I'm sorry. What's the unbiased estimator of the variance of P hat? Well, there it is, right? It's that thing there. So it's p hat, 1 minus p hat. P hat is 0.52. 1 minus p hat would be 0.48. The sample size was 50, so this would be 49. Then 1 minus 50 over 1,000. Okay. And what is this equal to? I don't know. 0.0045. Great. You did that in your head, or it's okay. Say it again. 0.0045.
Correct.
Okay. Okay, so let's find a 90% CI for P based on this data. Yeah,
So we assume there are 1,000 hospitals.
yeah,
total.
1,000 total. I think that's what that says up there.
That's
Oh, no, I'm sorry.
1,000 users.
No, I took the wrong number here. What was it, 392? 393.
Yeah. A sample of 50 of the 393 hospitals was taken.
Okay, 393, thank you, sorry about that. But this number was still right, and SP hat was, it says in there what it is, what is it? When he takes
0.067.
0.067. When you take square root of that, you get this. Okay, so let's find a 90% CI for P based on this data. So all we do is plug in the numbers here. Okay? So 90 is, first I guess you express 90 as 100 times 1 minus alpha. So it means alpha is 10, point 1, right?
Yeah.
Alpha is 0.1. Alpha over 2 is 0.05.
Yeah.
Z of alpha over 2 that means that there's a little switch in notation from here to the table for normals. Table 2 has this picture, and in the picture there's a number here, Z sub p, and Z sub p is a number so that the area under the normal density to the left of ZP, Z sub p, is P. So what was Z of alpha? That was the number so that the area to the right of Z of alpha was alpha. So how do we relate Z sub P from the table and the notion of Z of alpha? Yeah. Okay, from the table, you look up Z sub 1 minus alpha if you want to know Z of alpha. But actually, we want to know Z of what? Alpha over 2. So this should be 1 minus alpha over 2. Z sub 1 minus alpha over 2. In other words, we want the area out here to be alpha over 2, so that means the area over here should be 1 minus alpha over 2. Okay, in the table, they have this picture. So that means if we want to find where the area to the right of a point is 0.05, that means we should find the place where the area to the left of it is 0.95. So that's what you look up in the table, 0.95. And probably some of you remember this by now.
1.96.
I told you some of you would. .96, I think you're absolutely right. No, wait. We want, so what did we want? We want 0.95, right? Actually, you got 0.975. 1.96.
Oh, yeah. I think you need about 95% confidence.
Yeah. I think it's 1.65.
Yeah.
1.65 for this one. Okay. So Z sub 0.05 is approximately 1.65. Maybe it's 1.64. It's a little bit over. Okay. So just plugging in the numbers there. Let's see, p hat we got was 0.52 minus 1.65 times, well, we took the square root of this, right? It's this is SP hat, 0.067. And then 0.52 plus that number. Okay, I guess there's no point in computing these. You know how to put numbers in a calculator. But that's it. Okay. But I would like to know, does it actually contain the real mu? So anybody have a calculator? Can they compute this number and this number?
So the lower bound is 0.049, or 0.409, I'm sorry.
The upper is 1.62, 1.63. 1.63. Yeah.
That seems a bit much.
1.63.
This is less than 1.
Never mind what I said. Yes, sir.
I think you missed a decimal place.
0.63.
Yeah, I did.
0.63, okay.
0.63.
And the true value was 0.654. We missed. Well, that can happen. One time in 10. Okay.
Is that what it is, Mark?
Yeah. Okay. All right. That should build your confidence in confidence intervals. You can see that the sample mean was quite a ways from the true mean already. What went wrong? The sample size is pretty small compared to the population size, I think, here. Okay. So let's move on to ratios, estimating ratios. I think this is section 7.4.
Professor,
Yeah.
you were saying that 50 was too small a sample out of 393? Or 390, whatever it was?
Yeah, well, maybe it wasn't that small. Maybe we were just
Or maybe
unlucky.
the population
Yeah.
was not large
Yeah.
enough? Or
50 over 393. Actually, it doesn't seem all that small compared to 393. I think it was probably a matter of bad luck. You know, like you have 9 chances out of 10 to win, and you lose. I think you could say you had bad luck. Yeah. So something that can happen 1 time in 10 does happen. Actually, something that can happen with probably 1 in 10 million. That it does happen. Like somebody wins a lottery, right? Okay, so we have one population in this chapter. Of size capital N. And 2 measurements are taken on the individuals on this population. Okay, so x1 is measuring some quantity associated with individual 1, and y1 is measuring some other quantity associated with individual 1. So this might be something like how long that individual lives and how much coffee that individual drinks. Might be some, or how long the individual lives and how many cigarettes that individual smoked, or how tall the individual is and foot size, or I don't know how many cars, income, number of acres a farmer has, how many acres he plants corn, all kinds of things like this. I think some other ones are mean income of a family, SAT score of the oldest child. Okay, things like that. So you want to study how these 2 measurements are related to each other. Now, if I divide top and bottom by 1 over capital N, it doesn't change this ratio. So I could re-express this as the true mean for the y measurements divided by the true mean for the x measurements. And we'll be interested in estimating R by taking a sample. Okay, we'll need the population covariance. I'm sorry. Which is this? Okay, so what does this mean? We sample little n individuals, and we take their x and y measurements. Okay. A computation like the ones we did earlier today give that the covariance of the x bar and y bar is this. You just put yi's in everywhere where we had xi's. But we did the variance of x bar before, right? If you just do the same computations where you replace one of the x's by y's and carry through all the steps, you get this. Our estimator for little r, based on this sample, will be capital R. Which we can also write as x bar over y bar. Yeah.
So why is little r y over x and big R is x over y?
Oh, because I got confused. Thank you. Thanks for pointing that out. Okay. So we need to estimate the variance of R somehow. Okay. So let's do a little calculus, multivariable calculus. Did you all take 2E or D? I can't remember.
D.
D? How about E? Yeah, there's an E, yeah.
There's no prerequisites in the summer.
There's no prerequisites for this class?
Not in the summertime, no.
Oh, okay.
I don't think that was
Okay, so just I'll teach you everything you need to know then. So here we have a function of, suppose we have a function of two random variables, x and y, and we want to approximate the variance of that function of those two variables. Now these variables will assume we know these quantities. And we'll try to express this in terms of these guys. Okay, if we were in the one variable case, if we're in the one variable case, so we had some function of a random variable, we call it z. We want to approximate variance of z, and we know things about x, like the mean and the variance. Well, we write g of little x equal to g of mu sub capital X plus little x minus mu sub capital X times g prime of mu sub capital X plus 1/2 x minus mu sub capital X squared g double prime of mu sub capital X. And this is approximately equal for little x not far from mu sub capital X. This is just the second order Taylor expansion for g. If x has a pretty high probability of being near its mean, then this is a good approximation for g of capital X equals z. Okay, so what can we say then about the expected value of z? Well, it should be about like the expected value of the right-hand side. And what's the right-hand side when we take expected values? Well, the first term is a constant. That's just g at the mean, which is just a number. So we get g of mu sub x. What about the second one, when we take the expected value of the second thing here? This is just a number, so we factor that out. What's the expected value of x minus its mean? 0. The expected value of this term is 0. And then what's the expected value of this term? Well, the 1/2 and the g double prime are constants, so we pulled it out. So we take the expected value of x minus its mean squared. What's that? That's the variance of x. When we take the expected value of this term, we get 1/2 g double prime times sigma x squared. Now let's go to two variables. And let me call this, for simplicity, let me call this the vector mu, maybe. two-variable version of that, oh, sorry, g of xy. Maybe I should be a little, I differentiate g with respect to x here and then evaluate it at mu. Here I multiply by the derivative of g with respect to y, evaluated at mu. And then I get second order terms that look like this. And this is approximately equal. Okay, so this is a second order Taylor expansion for a function of two variables. You may or may not have seen this. You can compare with that. Okay, so what would we get then for, say, the expected value of the function of two of these? Well, we just evaluate this at capital X, capital Y, and then take expected values. Here we'd get g of the mean. Here I put in capital X, and I take the expected value of capital X minus its mean times a constant. What would that do? What would that be? That's going to be 0. Expected value of capital X minus mu x is 0. Expected value of capital Y minus mu y would be 0. So when I take expected values, these terms vanish. Expected value of capital X minus mu x squared is the variance of x. So I get the what happens here? I get sigma sub x squared over 2 times the second derivative in x at mu. Likewise, here I get second derivative, I get the variance in y times the second derivative of g in y. And then plus, what's that last term? That's the covariance of x and y times the mixed second derivative of g at mu. Okay. Right, so that would give you the expected value. In one-dimensional case, it looks like that. In two variables, it looks like this. What about the variance? Let's see if we can get the variance approximation from one-dimensional case. Well, what did we approximate this by? That's approximated by g of mu sub x minus sigma x squared over 2 g double prime of mu sub x. We square that. Running out of time. Okay, I'll leave the variance computation till next time because I want to get the. I want to apply. Let's go back to this. I'll do this if I have time today, but I want to at least get the expected value estimate for the ratio. So I'll continue this, but I think since I have 6 minutes left, I want to make sure I get at least one thing done. And that would be, will continue to be continued. See, this is a function of two variables now. The ratio is a function of two variables. So we should apply this formula to the function, what? G of xy equal to y over x. So what do we need about g? We need dg dx, dg dy, second derivatives in x, second derivatives in y, and the mixed derivatives. Okay, so let's compute those. Differentiating that with respect to x, we get minus y over x squared. Differentiating a second time with respect to x, we get another minus sign. So we get 2y over x cubed. If we differentiate this with respect to y, we get minus 1 over x squared. Okay. dg dy is 1 over x, and d squared g dy squared is 0. Okay. So using this formula here, applied to x bar and y bar, we get that the expected value of the ratio, capital R, is approximately equal to, we use x bar and y bar everywhere. So what would g of this rate be? It would be mu of y bar over mu x bar plus sigma squared x bar over 2 times the second derivative in x is 2 y bar over x bar cubed, right? Plus sigma y bar squared over 2. And then the second derivative of y is 0. Plus the covariance of x bar, y bar, times the mixed derivative, which was minus 1 over x squared. But that's evaluated at mu sub x, so it isn't mu sub x bar squared. So actually, I'm sorry, I made a mistake. This is at mu, so that's mu sub y bar over mu sub x bar. And this is, see, it's g evaluated at mu sub x bar, mu sub y bar. So in there you get sigma. So this is the sigma x bar squared term. So it means I have to multiply by this. So it'd be twice mu sub y bar divided by mu sub x bar cubed. Okay, see, it's 2 times the second variable over the first variable cubed. The second variable is mu y bar. First variable is mu sub x bar. And we get this. Okay. So expected value of r, replacing these by what these, mu y bar would be mu y, mu x bar is mu x. Here the 2's cancel. The variance of x bar can be, we'll replace it by sigma x squared. And then we get mu sub y over mu sub x cubed. And then we get, here we put in sigma xy, and then 1 over mu sub x squared. We can divide out by, we can factor out the mu sub x, and then you get a, let's see, I want to have a nice form of this. Maybe, yeah, we should keep this term here, and then this is sort of a approximation away from that. So let's write it in this form. Okay. So the expected value of the ratio is approximately equal to the ratio of the expected values plus this perturbation term. Now you wouldn't expect this to be equal to that, right? Which would be mu x over mu y. There's some correction term. This is the correction. Okay.
You need mu.
Well, I should do y over x again. Okay. This would be that thing. This would be this thing. Okay, but there's a sort of a correction away from that. And it's given by this term here. Okay, so I think there are some exercises. We'll do the variance of R next time. And then do confidence intervals for ratios.
When will you post the?
Yeah, so you can see what problems you have to do within an hour. I'll have those modified.